So the question now is that somehow this analog waveform, right, the waveform that we actually saw in this oscilloscope, which was around 1.75 volt, right, because of, I mean, that 1.75 is a property of this particular scope, okay, but anyway, there is some signal which is oscillating about a bias, okay, V bias, okay, and we have somehow been able to store this in a computer.
Yeah.
Okay. So the first question that we have to ask is, you know, if I plot this with respect to time, there is an analog signal value available for every time instant.
That's true. Yes.
Right. So if
Yes.
I look at it at after 1 second, yes, there is a signal. After 1.1 seconds, yes, 1.05, 1.01, you keep going down to whatever real number you want, however
Yes.
small, there is an analog amplitude available in that signal.
Yes.
Right, because that's how analog signals are by nature. So if I were to, you know, think of storing all this information somehow digitally, right, as a function of time, I want to store all of this. Do you think it is possible?
Doesn't seem like it, because you just said you go to any shorter and shorter period of time.
Yeah.
It sounds like you will always have a value there.
Yes.
You will have an infinite number of time points.
Exactly. Infinite number of time points,
Yes.
right? So it does not, we are not even talking about how we represent the amplitude yet.
Yes.
We are just talking about how many time points there are
That's
in
true.
that analog signal. And clearly that is infinite in nature, and therefore we cannot possibly store such a value. In fact, that's the reason why the analog oscilloscopes were not able to store the data.
That's true.
Right?
Yes.
So the first thing that you need to do in order to store anything on a computer is to sample it in time.
Yes.
Okay? So we will talk about time sampling.
Okay.
Right? And now, having discussed this, can you throw some more light on what this 44,100 hertz was?
I can take a guess.
Yes.
So we said there are infinite number of points. I cannot store infinite number of points.
Yeah.
I know I have to store a finite number.
Yes.
So now I'm just going to choose. Maybe I can choose points where it doesn't change so much, or at some point,
Yes.
right? At some finite instances of time, I'm going to store the values.
Exactly.
And hope that I can play back whatever I recorded, right?
Exactly.
That seems like
Exactly.
the hope.
Great. I think that's a very good guess. In fact, that's exactly what this sampling rate is all about. The sampling rate basically tells you, you take this time axis and discretize it. Okay? Maybe I'll draw that in a different color. Okay?
I think I understand now. If you say 44,100 hertz, I know that hertz is 1 over second.
Yes.
Which means for every second, I get 44,100 points.
Exactly.
Right?
Exactly. Right. So
Perfect.
if you take 1 second, I think that's a great way of. So let's say this is 0 and this is 1 second. Right.
Right.
If I sampled at, let's say I sampled at a rate of 1 hertz first. Okay. Then I would be getting 1 sample every second.
Yes.
Right. So I have, you know, 1 sample here, then the next sample here, the next sample at 2 seconds.
Yes.
And so on. Right. Now clearly this, you know, the rate at which we speak, in 1 second you can actually say a word, right. So it's very evident that 1 second or 1 hertz is just too slow.
It's just too slow.
Right. You are going to lose out not just frequency content, you lose out information of the sentence.
That's right. That's right.
Okay. So essentially you need to sample at a much faster rate, right. So that's why you see that the options that have been given there, they don't go down to like 1 hertz or something.
That's right.
They give you like 8,000 hertz. Right?
Exactly.
Yeah, 8,000 hertz, 16,000 hertz and so on. That's how it goes, right. So what does 8,000 hertz, like you said, right, in 1 second I can have 8,000 samples.
Wow, that's a lot of
That's a lot of samples, right? But you will actually see that's not enough
Oh, really?
later. Okay. So you can have,
Which is why the default must be at 44,100.
the default was 44,100 hertz, and in fact if you go a little back in time, this is what they call the CD sampling quality. The
I
CDs,
see.
audio CDs that
Yes.
used to come with this sampling rate.
I see.
And there's a very good reason for that. Later we will discuss those details,
Sure.
right? But effectively we are now talking of discretizing time like this, and in 1 second I will get first sample, second sample, third, fourth, like that, 8,000 if it is 8,000 hertz. Otherwise I'll have 44,100 samples, right? Now clearly, can you tell me if 44,100 will capture all the information that was there in 8,000 sampling?
I would think so, because you have more number of points, it would most likely capture all the information that was there in 8,000.
Right? Exactly. So so if you look at that, what it basically means is, if you take 1 over 8,000, right? So this is what I call the sampling time.
Yes. So that is the distance between two adjacent samples in the time axis.
In the time axis, right? And what is this approximately equal to what? 125 microseconds?
125 microseconds, right? It's correct.
Right? Yeah. Okay. So 10,000 by no.
Is that right?
1 million by 125. Right? Yes.
That's right.
1,000 by 125 and 1,000. Yes, correct. So we are talking of 125 megahertz. So the time gap between two samples is 125 microseconds.
Yes.
Okay. Now, if I sampled at 44,100 hertz,
Yes.
then the sampling time is going to be 1 by 44,100 hertz.
So 1 by 40,000 is already 1/5 of 125.
1/5.
So it's 25 microseconds.
Exactly.
So it is even smaller than 125 micro,
Yes.
right?
So if I sampled at 44,000, the next sample would be 1/5 of that,
Yes.
right? So this is approximately 25 microseconds.
Yes. In reality, it's a little bit small, slightly smaller than 25.
Smaller, but
right.
yeah, let's say
Correct.
25 microseconds.
Correct.
That means every 5th sample of the 40,000 hertz
Yes.
is going to be exactly like the 8,000.
That's right. Except
sampling.
that I've gotten 5 more points in between the two.
Exactly. You have 5
Right.
more points in between, which we can therefore say the 44,100 hertz has more information.
And I can see why as well. Because within the time instant, if my audio signal has changed,
Exactly.
I can capture that as well.
You can
because
capture.
whereas earlier I would not have captured it.
Exactly, right? So I think that's a great way of looking at it, right? And in fact, it seems to suggest that if you look at this, the waveform, right? How fast is it changing? So if you look at this oscilloscope here that we have said, right? It says 20 milliseconds per division. We are already in milliseconds, and you can see that that is changing,
Changing
right?
a lot, correct.
Now, if you bring this down to microsecond scale, right? You will find that the audio signal is not changing that much, right?
That's true.
It actually will change after lot of samples, right?
Yes.
And in some sense, that is what is being exploited here, okay? And students will later appreciate this when they study something known as sampling theorem,
Yes.
right? It's
That's
called
true.
the Nyquist sampling rate, and which will guarantee that the analog signal can be reconstructed completely.
That's right.
Okay.
I think that they will see after a couple of courses. I
After a
think.
couple of courses, right? But the intuition is at 20 milliseconds per division, right? If I even make this, do I have like 1 millisecond per division? You can see that it's, it's more or less constant.
That's right.
Right?
You don't see it changing so much.
Yeah. So if
right?
I sample at microsecond scale, I am going to get effectively like a constant signal, right?
Yes.
So if what we are effectively saying is, you take this small portion of signal, okay, which is.
I see what you're saying. So what you're saying is, if I go to a microsecond level time difference, the time representation
Yes.
of our voice is actually not changing from one sample to another sample.
Exactly.
Right?
Right. So if you look at this, this is how the audio signal changes,
Yes.
and this is in time, and this axis is, we are saying, is in milliseconds.
Yes.
Now microsecond is a thousandth of that. So if I take a small portion here
And magnify it,
and just
it'll be almost
magnify
flat,
it,
right?
right? If I just magnify it, this would effectively look like a straight line with a very small change in amplitude.
Right.
Right? So it doesn't matter if I sample it here or sample it here, sample it here, it's effectively a number.
Right.
Right? That is not
Right.
going to change. And if I sample fast enough, then I am going to capture these changes
Yes.
quite accurately. Okay? So that's what this 8000 hertz or 44,100 hertz means, right?
So if I were to take the 8000 hertz sampling, I might see some small change, whereas for 4400 I would be almost flat.
Yes,
That's what we are
okay,
saying.
but that again depends on the content that is being recorded. For
Right.
example, voice may not have a problem even with 8000 hertz.
I
right?
see, I see,
because
okay.
it depends on what frequencies our voice contains. Now, if you put a guitar in there and other stuff,
course.
then you have a problem. Because remember, with instruments, as we sort of discussed earlier, there's a problem of harmonics also.
Yes.
Not just the frequency,
That's
all
right.
the harmonics also carry information.
That's true.
And therefore, you must consider that frequency content as well. Okay? Yeah. So, one thing you can do is, if you look at this PCM signal, right? It's been recorded for a certain duration of time, right? We know what that is, right? Some 1 point something seconds. And if I tell you that it has been sampled at 44,100 hertz, can you tell me how many samples there are in that?
In how many seconds are you looking
Let's
at?
say 1.3 seconds.
1.3 seconds. Well, in 1 second I have 44,100. In 1.3 seconds I should have 44,100
Exactly.
times 1.3.
Right? So, first thing, right, is you can accurately calculate the number of samples in that wave file.
Yes.
Okay? It's
Yes.
called a wave file or a PCM file. If you know the total duration and actually know the sampling rate, it is simply going to be sampling rate
Times time of capture time.
exactly into T capture. Okay, and of course here I said it was sampled at 8000 hertz, so it's a different, you'll have different number of samples.
Yes. So makes sense, right? We said for every one sample at the 8000 hertz we have 5 samples.
Yes.
So the number of samples will automatically scale with the sampling rate. That also makes sense.
Right? So one thing we do notice already is we are talking of even 1 second of data,
Yes.
we are talking of like 44,000
Samples.
sample points.
Yes.
Okay, we have not even come to how many bits or you need to store that particular value and all
Yes,
that, right?
yes.
But just that number of samples is very large. Okay, so if you take an average song which is like 4 minutes or so, right? There are like the wave file when it's written out, okay, may come out with large number of samples.
Now I see why people spent a lot of time working on compression, like MP3 and
Exactly.
The history of from wave to MP3 and so on is well known.
Exactly,
Correct.
right? Because the wave file in its raw format just consumes a lot of space just to store all these samples.
Yes.
Okay, and that's why, like you said, the MP3 format became very famous.
Yes.
But let me tell you that the music directors hate it.
I see.
Because it completely kills the quality of the sound.
Oh, I
okay?
see. Okay.
Those guys are looking for like some 10th harmonic of that drum beat, of that guitar beat, which is simply not there. It's just eliminated in MP3.
Completely.
Okay, so the wave file with highest sampling rate is what will actually hold all that information together.
So CD quality.
CD, not even CD, it goes higher, 48 kilohertz,
I
96
see.
kilohertz.
I see,
Right?
okay.
So that the harmonic content actually holds all that information for the music directors. And I remember an article by A.R. Rahman where he actually spoke about the need to actually, store this music in its highest quality.
I see.
And not as MP3s.
Okay, okay.
Yeah. Anyway, so let's come back to this discussion. So effectively, let's say we are going to sample, let's pick 8000 hertz because it's a nice number, right? It translates to 125 microseconds, okay? and I am looking at some audio signal, okay, which is sort of slightly, I will plot it like this, right. I am going to now sample this pretty densely, okay, and throughout the duration, okay. So what I have now is my time signal x of t has now been represented by discrete numbers in this.
Yes.
Okay, Ts is my sampling rate. Okay, sampling period, not
Sampling
rate.
period.
Yeah, rate is in hertz.
Yes.
Ts is
So, yeah.
Ts is
Yes.
this. So Ts equals. Okay, maybe I'll call this sampling frequency.
Fs.
Okay,
Perfect.
So n. So now this time
N refers to the sample number.
exactly. So for example, this sample is n equal to 0. This is n equal to 1. This might be, for example, n equal to 100.
Yes.
Right. So like that, what we have done is we have taken this time signal, which is a continuous. Remember, we said we had infinite number of
Yes.
time values,
Yes.
right? But now we have reduced this to a sequence of numbers, x1, x2, like that, and we know how to how many samples there are.
Right.
So it would go all the way until that value.
Okay.
Number of samples, if I say n is equal to this, I have a sequence of numbers x0, x1, x2 all the way to x of nts, right?
Yeah.
Now at least it is possible to think of storing this because we have finite number. Yes, it may be large, it may occupy a lot of space, the file size may be huge, all that doesn't matter, but we can store it. Okay.
Perfect.
So the first thing is we had to time quantize.
Yes.
Okay.
Yes. Actually, I have some intuition on this.
Yes.
So I'm thinking, if my input signal did not change, let's say I took a DC voltage,
Yes.
right?
Wow.
And I wanted to find out how many samples, if I sampled it at 44,
Lovely.
right?
Yeah. Yes.
44,100 hertz
Yes.
versus 8,100 hertz.
Yes.
It seems like it doesn't matter because the DC value, the value is not changing versus time.
Exactly.
So even if I did 1 hertz sampling
Yes.
or even half a hertz sampling,
Exactly.
right? I would get the same value.
Exactly.
So literally I need only one sample
exactly.
to store a DC.
Right. That is the point. So if you
Right.
took a DC value, there was nothing there.
Right.
All I needed was
Any one sample
x
at any one
of
time.
0. Right.
Right.
Okay.
Right. And if I took now a very slowly varying signal, right? It means I need smaller and smaller number of samples.
Samples.
That's what it seems like.
Exactly.
Right? Because if I choose a particular interval, if the signal doesn't change,
Exactly.
that
so,
means.
So let's say I have a slowly varying
Yes.
sinusoid like this.
Yes.
Right. Then you might say, yeah, I need to capture something here. Right.
Yes.
Something here
Correct,
and
correct.
just a couple of samples
Couple of
like
few
this.
samples. So it seems like if I have a slower signal, so DC is actually very slow, it's not changing at all.
Yes.
It is so slow that it's not changing.
Yes.
And it seems like I need literally one sample.
Yes.
And if I choose a very slowly varying signal,
Yeah.
I probably need a very, very low sampling rate.
Exactly.
Right?
Exactly.
So the faster the signal, the higher the sampling rate I require. Is that intuition right?
Absolutely, absolutely, right? And that's why I was saying earlier that for the voice, 8,000 hertz will
That's
still
right.
be okay.
Now I tie it
Because-
in with what you were saying. You were
Yes.
saying that you need to keep track of harmonics with a
Harmonic.
higher frequency.
Exactly, right? So even if you say we have a fundamental of like 200 hertz, 300 hertz, the 10th harmonic will be 3,000 hertz,
Yes.
which is, and 8,000 is still above that.
Yes.
And therefore it may be okay to sample a voice at that rate.
Yes.
I think even a female voice may be okay because that's shriller, it can
Yeah.
have a higher frequency content, but even there it may be okay.
Okay.
Right? But guitar and other thing, no, all bets are off. Right?
Okay.
That you have to go to 44,100 hertz. Okay.